maybe some.
Perfect.
Yeah.
So thanks again. The story I would like to tell you today is basically a story of one theorem that we with Jan Derbisz, Tomek Krawczyk, Jana Nowotna, and Karolina Okrasa proved last year. And that's a theorem and paper that appeared on IPEC last month. And this is providing an FPT algorithm to vertex deletion into this particular class of graphs, which are bipartite permutation graphs. And what I want to do is to give you not only the statement and the context, but some insight so that you can feel the flavor of what reasonings, what graph theoretical reasonings are behind. Okay, one technical thing, if you have any questions or you believe that something that I said is not right, then feel free to interrupt me and ask whenever you like. Okay, so the structure pretty much follows from the title. So first, I'm gonna tell you something about vertex deletion in general. Then I'll introduce you to the bipartite permutation graphs, and then we proceed on to the method and to the algorithm. Any questions so far? Okay, so let's start. So first, vertex deletion is a classical problem that most of you probably is familiar with. But let me recall that we are given a graph, say it's a vertex graph, and we are given a graph class that we are interested in. It could probably, for example, be a graph class that admits better solutions to some classical problems than the general. Like if they are in general NP complete, we can restrict our attention to a graph class, and we have the better ways to do it, and so it's natural to try to try to detect how close to a particular graph a graph is. And in classical setting, the vertex deletion, we want to find the smallest possible set of vertices whose removal gives us a graph which is in our favorite class. But it's in general, yeah, so first of all, we are removing vertices, so reasonable classes to consider are classes close under the leading vertices, so hereditary graph classes, in other words. But this is in general NP complete when the hereditary graph class is non-trivial, so it has a series of infinitely many non-trivial different connected components involved in in the class. Then it's NP complete to find the smallest set whose deletion leads to our favorite class. So it's natural to take parameter k and to consider a problem whether we can remove at most k vertices to get into our class. And this problem, parameterized by K, has received a vast interest in recent years or decades. So let me show you where the question came from. There are several important graph classes, as you can see, subclasses of perfect graphs, which are important, particularly from parameterized point of view. And also which are important from point of view of theory of partially ordered sets. I don't know how much are you involved into this stuff, but some classes that you can see here, for example, permutation or comparability graphs, are very tightly connected with poses, particularly two-dimensional poses, and those are also combinatorial structures whose structure and nature we want to understand, and we want to be able to edit our objects to fit into them. So this was our main interest, to understand permutation graphs, for instance, and in context of ordered structures. And this was also complete somehow this picture, as for example, bipartite graphs are proved to have FPT algorithm of vertex deletion. This is fancy called odd cycle transversal. And that's, I guess, among these graphs that you can see here, the oldest result that we have. It's been proved that for chordal graphs, we can also have an FPT algorithm. I can see a raised hand, so maybe let me stop here for now.
Yeah. Okay. So I just have a quick question here, just to clarify. So the way you have given this picture, so essentially it is like the proper interval graph is a subclass of interval graph, that is a subclass of chordal graph, and so on. Similarly, here in this case, based looking at the picture, permutation graph is actually a subclass of both comparability and co-comparability, while bipartite graph is also actually a subclass of comparability graph. If okay, right, I see.
That's correct. Yeah, thank you for this remark. I didn't say it. I should have said it. Yes, this is yeah, this
okay.
this excuse me. Are you continue asking another question? Yeah. So that's right. This picture is a poset of inclusion of classes, right? So we have an arrow from a class to a class if this preceding class is a proper subclass of the class pointing to. Yeah, thank you for this. Okay, so in particular, we have chordal vertex deletion FPT, but on the other hand, it's been proved that for that the class of perfect graphs, the entire class of perfect graphs doesn't admit an FPT algorithm. It's or it's highly non-probable. Yeah, it's W too hard. So there is this dichotomy present here as well, and it's following years. It was proved that for interval and proper interval graphs, one can also find an FPT algorithm. And what we did is basically coloring this rectangle blue again, providing an FPT algorithm for bipartite permutation graph class. And okay, and let me remark one more thing here, namely, recall that hereditary is nothing but close under vertex deletion, and the very handy tool in working with hereditary graph classes is the following equivalent characterization. So close under vertex deletion means closed under in just subgraphs, and is also characterized by a family of minimal induced subgraphs. So for all those classes and many more, for each hereditary graph class, you can compile a list of these minimal forbidden structures, and it will come in handy later on.
There's a question in the chat.
Yeah, I can see. I just opened this. Is permutation graph? Yeah, it's open. So the white classes here in my picture are still open, at least to our knowledge. And this bipartite permutation case is somewhat is meant to be a step towards understanding this more general classes, like for instance, permutation graphs. Yeah, and going back to these families of parameterized forbidden induced subgraphs, it's easily seen that a simple branching reasoning could be used to obtain an FPT algorithm whenever our class is finite. And it was given by Sai in late 90s. And it goes as follows: if the collection of our forbidden structures is finite, in particular the largest structure has a finite size bounded by some number, and we can easily see that this is actually the order of polynomial in which it is FPT, right? Because we need to only to search whether this forbidden structure is present of bounded size in our graph, and branch over all possible deletions of one of its vertices until we run out of our budget. But all the classes that you can see in the picture seem to have infinite families of forbidden minimal substructures, which makes them more difficult to provide an algorithm with. Yeah, okay, so this is the big picture on the vertex deletion problem. And I suggest we move to the small picture of bipartite permutation graphs, so the class that we're interested in. And let's introduce it via this forbidden induced subgraphs. So as the names would suggest, bipartite permutation graphs are precisely intersection of bipartite and permutation graphs. So let's first ask ourselves, what are permutation graphs? And permutation graphs in terms of minimal forbidden induced subgraphs are those. So it's a list of 9, about 7 vertex graphs and 7 infinite families of graphs. Which in particular contain all cycles of length at least 5. Here, yeah, the picture has been redrew from graph classes here, and as you would expect, this is quite an complicated structure. But fortunately, we are considered bipartite permutation graphs. So in order to have a list of all forbidden induced subgraphs for that, we need to add all odd cycles to it. So we need to add a triangle because that's the only one missing. And you'll see that almost all infinite classes will no longer be there because they would contain triangles. We are left only with an infinite collection of long cycles and several small finite graphs of bounded size. So this is the ultimate collection. Okay, another question I can see.
Yeah, can you please go back to the previous slide? Just yeah, no, even yeah. So yeah, here you have okay. Look at this particular obstruction. That the first one where some 2n+4. What is this 2n+4? This n+2. This thing stand for?
Yeah, I'm sorry. That's like the part of the picture I also didn't refer to. It's like the number of vertices within this infinite class can be any number of this form when n is a non-negative integer. So we only forbid graphs of this structure when where this this collection of vertices ranges in 4, 6, 8, and so on.
Okay, so 4, 6. Okay, just still there is some confusion. So for example, look at this first obstruction where say you have a triangle. Then how many triangles can there be? Means and then with 2 different pendants attached to the 2 terminal triangles.
Yeah, I should. Okay, so the numbers, this n and so on, would stand for those collections, and all those. Actually, to be honest, I'm not sure how to define those classes because we wouldn't need them. I just draw it to use to like signalize that the complexity of the entire family for permutation graphs. You can find the detailed description on the webpage graph classes, which contains all those classes with forbidden minimal subgraphs. And I will do that as well, but I'm not sure how to distinguish between consecutive vertices for now. So how are they connected to the other?
Okay, fair enough. So these these obstructions that are shaded with yellow color, and what about the other obstructions that you have kept? Are they the complements of these yellow shaded obstructions?
Yeah, and apart from the ones that are drawn here, all complements of those graphs are also obstructions, but they happen all to contain triangles. Maybe instead, maybe not for the complement of 5 cycle, which is a 5 cycle itself, but all other do have triangles. So when we add this forbidden triangle, they disappear.
okay, so essentially in this slide, whatever pictures are you have drawn, all are actually obstructions.
Yeah, I've drawn like a lot of graphs in order to make this reduction by intersecting with bipartite class visualized, so that we get rid of many forbidden structures which are in permutation graphs, and we don't need to no longer need to handle them in our bipartite permutation graph class.
I see. Okay, fair enough.
Yeah, thank you for the questions. I should have mentioned it before. But now, as we have this nice small family of forbidden structures, yeah, we have defined the bipartite permutation graphs by this. So these are precisely graphs avoiding those four small graphs. So triangle and this 3-7 vertex graphs, and avoiding long induced cycles, right? So we will call them holes traditionally, by the way. So for 5 and above. Note, however, that we can have 4 cycles, and they are of high importance here, and they make this class non-trivial. However, there is another characterization of bipartite permutation graphs I would like to show you, which is via orderings of vertices. So this is like the way to connect it with this posset world. And in order to give this characterization, let me give you first some definitions. So given a connected bipartite graph and a linear ordering of one of its parts, we say that this ordering has the adjacency property of this part if whenever you take a vertex from the other part, its neighbors are actually consecutive in this ordering of W. Okay, so as you can see in this picture, whenever you pick a vertex from U, its neighbors are consecutive in this ordering induced by W. And that this is an adjacency property, so I guess quite suggestive name. And another property that you can define for such an ordering, a linear ordering of one part of the graph, is something which is called enclosure property, which is whenever you have two vertices such that neighborhood of the first one is contained in the neighborhood of the other one, so this is the picture, then the difference between the two neighborhoods is connected. So we cannot have a situation like this. Let me draw that we have one vertex whose neighborhood looks like this, and another vertex whose neighborhood is inside, leaving vertices on both sides of this ordering W. So it's like to the very end of this interval defined by the larger neighborhood. This is enclosure property, and it turns out, surprisingly, that bipartite permutation graphs are precisely those bipartite graphs whose every connected component, right, admits an ordering of one of parts and symmetrically of the other part as well, that satisfies both these properties, so adjacency and enclosure. Okay, so in other words, bipartite permutation graphs are precisely the graphs that you can embed in a strip, say a strip of paper, vertices on both edges of this strip, in such a way that neighbors of vertices from one edge of this strip satisfy the enclosure and adjacency properties on the other part of the strip. Yeah, the edges being the bipartite classes and bipartition classes. And it turns out that those two are equivalent. It's been proved in the late 80s. And this gives a quite nice, this variety of ways to tackle the graphs. So via this ordering of vertices. Okay, so this is the adjacency and closure property and characterization of bipartite permutation graphs via embedding in strips, in rectangles. And that's the starting point of the story. So let me ask whether there are questions for the first two parts. So vertex deletion and bipartite permutation graphs. Okay, so yeah, there is no ordering for U in the definition. However, the definition is symmetric with respect to U and W. So when we once order the edge, the W edge, we can also like switch places of U and W and order the edge U, right? So in fact, we can assume that there are both orderings, and the properties of adjacency and enclosure work in both directions. Because in this picture, we don't care about the order downstairs at all. So we can flip the picture and order the other way, the other edge similarly. There was a question whether ordering on U exists as well. So we have this symmetry of both bipartition classes. Cool. So the method. Yeah. Okay, probably some noise. So our method is as follows. We define something which is so-called almost bipartite permutation graphs. So we proceed this way. We can do branching, whether we have a finite number of forbidden subgraphs, but we have infinite family. So what can we do? We can branch out some finite subfamily and be left only with long cycles. Okay, so we can branch out the cycles of small size. And actually, we prove some structural theorem for graphs like this that are necessarily without the four finite graphs and without some small cycles. And that's how it would work. It's a method based on one that was used for proper interval graphs, where also they got rid of all forbidden substructures, but for long hauls, long induced cycles. Yeah, and after we branch out the small forbidden subgraphs, so we remove them, we prove that our resulting graph has a nice structure. And we can apply this structural result to I'm sorry, this is my coffee machine. It will not be viewable in a moment. It would allow us to provide a 9 to k times n to the 9 algorithm for k vertexization to bipartite permutation graphs. And we can also slightly modify this result in order to obtain a 9 approximation algorithm. It's basically the very similar reasoning based on this structure. So let me formally define what are almost bipartite permutation graphs for us now. These are almost bipartite permutation graphs, where this almost refers to getting rid only of small cycles, of small lengths. Okay, so I can see a question whether 4S is bipartite permutation. It depends on whether it contains this T2 as a subgraph or not. So a generic forest not necessarily, because it can has this as an induced subgraph. Okay, so our almost bipartite permutation graphs are precisely graphs characterized by this finite family of forbidden subgraphs. So this is a class that we can reduce an arbitrary graph to by an FPT algorithm. And what we prove is that actually this word almost, when defined in terms of forbidden subgraphs, may be considered almost in terms of this ordering of vertices. So look what happens here. We are allowing long hauls in our graph, but nothing else. Only long holes are what it distinguishes between almost bipartite permutation graphs and actual bipartite permutation graphs. And it turns out that we can prove that whether we get rid of those short holes and this 4 or 3 forbidden graphs, then the resulting graph, each connected component of the resulting graph, may be represented in a similar way that the bipartite permutation graph, but this time it's not a rectangular strip, which has a beginning and the end and linear orders upstairs and downstairs. This time it's either a cylinder with these orders being cyclical in both up and upstairs and downstairs, or it's a cylinder with half twist. So it's a graph embeddable in a Möbius strip when you have this cyclic order going along the boundary. So in other words, our almost bipartite permutation graphs turn out to be bipartite permutation graph after you cut this strip somewhere and you unfold it to get a rectangle. So what we prove is that the remaining forbidden structures, these long holes of length 10 and more, actually all of them go along this structure, this strip defined somehow, and whether we can cut it in with a small local, when we remove local number of vertices, a small number of local vertices, and we are left with a bipartite permutation graph. To sum up, the main structural result that I would like to tell you about is that almost via forbidden induced subgraphs implies almost via orderings. And note that when we have this structure, we can basically find the whole hitting set. So the set hitting all remaining forbidden graphs in bipartite permutation graphs within this small local window, with whose removal allows to unfold it to a real bipartite permutation graph. Okay, so let's dive a bit for now a bit into details of this. So let me show you how to argue from left to right here. What's the idea? And then turn this idea into an actual algorithm. So we restrict our attention to a connected component of an almost bipartite permutation graph, which is not a bipartite permutation graph. So it does contain a long hole along this cycle. What we can prove is that this, and actually every long hole existing in our graph, almost bipartite permutation graph, is a dominating set. So the entire graph lies around this hole at distance at most 1. We can take shortest hole, one of the shortest holes, actually to build a structure around it. So say our shortest hole is of length 10. We can, 10 is even, so it's like easier to tentatively draw this shortest hole like this. So anticipating our bipartite structure. Yeah, and after taking this shortest hole, we can prove that actually there are only 2 types of incident to this hole. So we know it's dominating, and every vertex lies somewhere around, but we can prove that it actually can be of only 2 kinds. So it's either connected to precisely 1 vertex of the shortest hole, or 2 which are 1 apart. And this is only possibility for all remaining vertices of our graph. So this is quite a strong structure. And this allows to partition all the vertices, all the remaining vertices into classes like this. If it was an odd length of the shortest hole, then you will have a half twist somewhere around, and it would resemble this Möbius strip structure. And after doing so, we can prove that actually the structure of our graph is local in the sense that all vertices have their neighbors only nearby. Okay, so the neighborhood of this vertex is entirely contained within the classes that are on the other side of the picture, but close on this strip. And similarly for vertices of the other kind. Okay, so knowing that neighborhoods are local, we can actually use our forbidden subgraph. I'll show you a bit a glimpse of how to do it in a second, to get this adjacency and enclosure properties locally. So let's forget about what happens on the other side of our long haul. Okay, after we forget about it, we can actually prove that this local collection of vertices satisfies this ordering properties, which allow to see this bipartite permutation graph. Yeah, and after we merge the orderings, which are constructed locally, into a long or two long cyclic orders, these circular orderings, we actually get what we want. So this statement that after we remove several consecutive classes of vertices, and we get rid of all edges between the two sides of the removed part, then after unfolding, we get a real linear ordering satisfying the adjacency and closure properties. So in other words, if we consider a window to be such a collection of adjacent classes of vertices, let me remind that the classes are with respect to who is my neighbor on the shortest hole. Okay, then removal of such a window actually kills all remaining long holes. So there is no long hole connected, looking like this, for example, because we proved that after removing a part of our graph, this connected part on one side, what we get outside has this adjacency and closure properties, so it's a bipartite permutation graph, so it's hole free. Okay, and we can actually prove more, namely whether we consider wider windows, that we can find a minimum size hole heating set. So not only by removing small windows you can get rid of all holes, but also if you take any minimum vertex set that hits every long cycle in the graph, then you can be sure that it's contained within this 5 consecutive blocks of types of vertices. And after we know that, you can see that we can actually find this minimum size hole heating set by repeatedly applying separator finding within such a hole. So let me be more precise. If we append to this graph induced by this say window of length 5 a source from this side, anything from the other side, and connect it accordingly to whether we have a neighbor or not on the remaining part of our structure. And we do some classical gymnastics by modifying vertices into edges and turn the window into a flow network. Then we can use a flow algorithm actually to find the minimum vertex separator within this blue window, which is a separator from the left side of our cylinder and the right side. So it's hole heating. So let me say it one more time. When we found minimum vertex separators in all such windows, and there are only linearly many of them, and the flow algorithm is polynomial, then taking the minimum size one, we can be sure that this is the minimum number of vertices that we need to remove in order to get rid of all remaining long holes. So that's precisely the answer for the question whether our budget is sufficient for removing all remaining forbidden subgraphs or not. Namely, the thing that our that our whole heating set can be proved to be local. This window cycling. Okay. I know that this is like from high level outline, but yeah, I guess at least conceptually, it's nothing more than this on this high level. Like on the technical level, there's this finding of forbidden structures in there, and digging the structure more and more in order to get this nice orderings and this facts about local optimal whole removal sets. But that's pretty much the idea. So are there any questions to this idea?
I have one question, one small clarification here. I don't know if I have missed it. So here you have said that this thing, this window, this is something, means there is some, there are some collection of separators that you have to take as part of the solution or something like that.
Yeah, precisely. That there are two things. First thing is that we can prove that the optimal solution, which removes the smallest possible number of vertices, is local, is contained within a window. And the other thing is that when we have a window of say with 5, then we can in polynomial time find this optimal solution by flow algorithm, max flow min cut algorithm.
Okay, so it is not the case that means you may have some n power k many possible windows and those things you can pick, or you have to use something else to find some appropriate exactly which particular window you want to pick as part of the solution.
I'm not sure if I understood correctly. Maybe there. Let me try to phrase myself in a different way. We can also we can only like have a look in each possible window, right? And it's still a polynomial cost, and we are sure that the smallest solution found in all those windows is the optimum solution by this fact that it is necessarily local. It's not something obvious, it's something we prove. Yeah.
Okay, fair enough.
Okay, thank you. Okay, so let me be a bit more precise on. Okay, are there any other questions?
So I have a question. Am I audible?
Okay.
So the question is that so there is this thesis by Michel Dom on FPT algorithms for matrices with consecutive ones property. So is this so basically the way I look at the permutation graph deletion problem is that you consider a matrix. The rows are the vertices on the left hand side and the columns are vertices on the right hand side. And you have to delete a combination of rows and columns so that the matrix becomes consecutive ones property. Is that correct?
To be honest, I'm not entirely sure, as I don't happen to know the thesis that you mentioned.
Okay, then I will just post it in the link and then maybe.
Yeah, I'll be very grateful for a link to this. It sounds really interesting. I'm sorry not to provide a proper answer, but I'm not familiar with this one, and yeah, we didn't think in terms of matrices here, but it sounds like a thank you, like a nice idea to consider. Okay, so let's have things in order to let me repeat the algorithm, the entire algorithm precisely, and argue why it's FPT. So once we are given an instant of bipartite permutation vertex deletion, what we do is we do this branching in order to reduce our graph to an almost bipartite permutation graphs. Yeah, so either in all branches we run out of budget and still have some forbidden structures, this almost bipartite permutation forbidden structures, so one of the 9 graphs that are forbidden, the small cycles and the other ones. Yeah, or we get this set of this is oh, thank you for the link. Or this set of instances which are on the whole equivalent. Yes, so after we remove all the forbidden structures for almost bipartite permutation graphs, in each leaf we're left with some smaller budget in order to turn it into a bipartite permutation graph by removing long hauls. And what's important here is that, yeah, actually our set of forbidden structure for almost bipartite permutation graphs is of bounded size. Each of them is of at most 9 vertices. So our branching tree has at most 9 to the k leaves. Yeah, and looking for a forbidden structure in each turn, we pick a set of 9, at most 9 vertices of our n vertex graph. So in total, this part is of order 9 to the 9 times 9 to the k. Both 9s being the upper bound for the size of a forbidden minimal structure. And once we are left with this set of reduced instances, we know that they are almost bipartite permutation graphs, and we want to remove the long host from them. So we, yeah, for each connected component within such G prime, we find this minimal size of whole heating set by this looking through all possible windows and picking the one with minimum vertex separator. Yeah, by this flow algorithm. And after we do it in every connected component, we simply add up the results. So in order to get rid of long holes in this graph, which is not necessarily connected, we add up the results for all connected components and compare them with our K prime. Yeah, and that's it. And from theory of flow networks, this is time O of n to the 6, so less than n to the 9th. And in total, the complexity of our algorithm is as n to the 9th in n. Yeah. Okay. So that's how it works. So first is branching in order to get rid of small stuff, and then hitting long holes by this structural theorem that we prove. And as I promised you some flavor of what is the reasoning, let me show you how to prove some bricks in this outline of structural theorem for almost bipartite permutation graphs. So, for example, the holes being dominating follows from this forbidden subgraphs quite directly. Yeah, so if we take a connected almost bipartite permutation graph and a hole within this graph, so we have vertices here. Then if it's not a dominating set, then we need to have a vertex of distance 2. Okay, as it's not if it was not a dominating set, that we would have a vertex of distance 2. And now, okay, so it doesn't admit any connection with the hole. And if we have a look at this vertex and these 2 possible connections, yeah, then you can see that if none of them is an edge, then we get this forbidden structure in here. Okay, and if one of them was an edge, then we would get this kind of forbidden structure here, knowing that the shortest hole is long enough, yeah, because it's of length at least 10. So that's an easy lemma proving that holes are dominating in our class of almost bipartite permutation graphs. Yeah, and maybe this think about the structure of around the shortest hole. So if we take a shortest hole, the one that was green on my previous pictures, yeah, as I told you, we can prove that every other vertex, we know that this hole is dominating. We know that every other vertex is either neighboring with only one vertex on this hole or with 2 of distance 1 between them, with one vertex between them. And it follows from this, when we have any other vertex in our graph, then we know that the hole is dominating, so there is at least one connection. If there is exactly one, then we have what we want. And if there are 2, then at least 2, then if we cannot have 2 neighboring, because that would yield a triangle. We can have 2 of distance 1, and this is what we want. But if on any place on this hole, along this hole, we had distance at least 2 vertices apart from one to the other, then what we will get is a shorter hole. Yeah, so this contradiction is from the green hole being the shortest one, and this allows us to make this reduction. Not only reduction, but the only possible case that is left is that this extra vertex is connected with every second vertex on our shortest hole, but then we have again our forbidden structure somewhere in there. So here as well, this strong structural claim is quite readily seen from the definition of our class. And displaying with forbidden subgraphs can be done very carefully in order to provide the disordering things. Yeah, there is one more thing. I'm not sure if how well I could explain to you, but maybe let me just draw this picture that once we know that our graph is embeddable in this, say, cylinder, yeah, or a Möbius strip, and we know that after we cut the fragment of the strip in order to so that what we are left with is a bipartite permutation graphs, it doesn't necessarily tell us that our holes cannot look like this, so go around it twice, because we will hit this, but this hole is not like of the same type as the shortest hole. So we can actually prove that all long holes that stay in the almost bipartite permutation graphs are, say, homotopic to the shortest hole. So they go around this structure exactly once. Yeah, and this is again done by some ordering arguments, like if the hole was turning back, then we would find this forbidden structure. So it must go along. If it was hitting again between 2 nodes that previously were there, so trying to start this other lap over the structure, then we could get a chord in our hole, so it would no longer be an induced cycle. Yeah, and the stuff like this happens here. Yeah, I guess the most interesting proof is the one that this separators are local. Yeah, so the optimal hole hitting set is not spread around the entire strip, but it's concentrated within some local group of vertices. Yeah, let me just tell you that This is proved by assuming it's not, and showing how to refine a whole existent, whether we remove one vertex from our minimum potential minimum separator in order to be omitting this minimum separator. Yeah, so after we assume that our local set is after that our local set is not contained with is within short window, then we get a contradiction by removing one vertex from this potential heating set, finding the hole because it was minimal, and adjusting the hole in order to be omitting the set again. So a hole outside of this heating set. I know that it was like quite hand wavy. So maybe if there were questions, I could elaborate a bit more about this. But for now, let me go towards the conclusion of what happened there. And in order to give the conclusion, let me give you the picture one more time. And it was that there was this question already. What about these blue rectangles? And let me repeat the question, but then color them green. And green stands for we don't know. Yeah, so as you see, as you've seen before, the collection of infinite families of forbidden structures for permutation graphs is really large and really sophisticated, and there are many different infinite families. Yeah, our cycles would stand structurally for this gluing this strip together, right? So in order to get a cylinder or a Möbius strip. But if we have this other variety of infinite structures, yeah, I mean, we don't know what should they correspond to this picture-wise. So this is permutation graphs, and for comparability graphs, it's also difficult to catch this structure of the family of forbidden subgraphs. We can think, one can think of how could almost permutation or comparability graphs look like. So we can again branch out the small structures and be left only with the representants of large size of the infinite families. Yeah, but now it would be nice to have something like this theorem of Spinrad this one about embedding into strips. We don't happen to have similar, I guess, theorems, or do we? Maybe we do. Actually, another definition of permutation graphs is something about intersecting segments. But maybe it can be adjusted to state some structural almost theorem, who knows? And there is this context of posets, which somehow grows perpendicularly from this scheme towards us in another dimension, which is the classes here are very more related to very much related to so-called two-dimensional posets. For example, our bipartite permutation graphs correspond one-to-one to two-dimensional posets of height 2. And comparability graphs, I guess they are graphs of two-dimensional posets themselves. So the parameterized complexity in the world of posets can be done here as well, and it is nice to see what is the structure of two-dimensional posets. The only difference is that we have different things on input, because now we have a generic graph, and in the poset world we would have a generic poset, which graph-wise is a comparability graph or something like this. So we have this direction there. Yeah, and as you can see, there is still much to be done in the area. I guess that's a place when I can place a full stop in. Thanks for the attention, and I'm happy to answer questions if there are some.
Thank you for the talk. And yes, we are open for questions. If anybody has questions, you can just unmute yourselves or ask, or if you wish, you can type in the chat.
What about the polynomial kernel question for bipartite permutation graph deletion? Is that also open?
Thanks for this question. Actually, we've been thinking a bit about kernelization here, and there are some attempts, I guess, to use techniques that have been used in similar problems concerning different classes, like the irrelevant vertex, for example. It's one of them, and we are quite sure that it should work, but it's not digested enough yet.
Okay.
Also, I can tell you that other graph addition problems like edge deletion, edge completion, edge modification are like could be done for bipartite permutation graphs in a similar way, but they are another level of technicality needed is for this, because we need to consider edge cuts instead of vertex cuts.
Also, just one more quick, maybe a bit silly question. So, for example, bipartite graph is not just hereditary but also closed under subgraphs. It means that even if you delete edges, still it remains bipartite, but that probably doesn't hold for bipartite permutation graph, if I understood correctly based on the obstructions, etc., that you gave in the picture. Actually, it does not, because those that some kind of some T2 or some such kind of 7 vertex obstruction you saw, that is actually you may delete edges and still may be able to get somewhere like that.
Yeah, thank you for that. Actually, in the in bipartite permutation graphs, there are a lot of these T2s and X2s which are not induced, this extra edges which form C4s, for example, helps us in maintaining the structure there.
Okay, yeah, okay, fair enough. Just another question, just for curiosity. So, okay, so there is some other graph class called as caudal bipartite graph, where just by the definition, it is that it is bipartite and does not contain an induced cycle of length at least 6. So how is bipartite permutation graph and caudal bipartite graph, these two graph classes related? Maybe they are non-trivially different graph classes.
Thanks for this. I must say I'm not sure, but this sounds like something that would fit in this picture, like somewhere between
true.
the arrow. I think maybe first of all, there is no clear connection between this inclusion or this relation between classes and the answer, because we don't have any simple, if this is a PT, then this one is as well. But I must check, to be honest. I don't have anything about bipartite caudal graphs in mind right now. But I think this is very interesting a question to be asked here, and it is quite hopeful to get some structure in there as well. As you said, this family of forbidden graphs is really nice to handle.
Okay.
I'm not sure if thoughts on permutation graph vertex deletion. Actually, about permutation graph vertex deletion, maybe I can tell you that our entire the research that yielded to this result started with permutation graphs, and they turned out to be not easily accessible. For example, by this very complicated family of forbidden induced subgraphs. Well, we've tried several different characterizations, but they didn't seem to give anything that could be successfully, at least by us, taken to another level of understanding.
All right, then I guess this is it. So yeah, thank you once again for the great talk. It was really nice to have you, and thanks to the audience for being around. So we close our seminar for today and see you all next week. Thank you. Bye.
Thank you.